I think we'll send you a nice flag for your time.
Okay, thank you.
And thank you so much for being here today with us.
Thank you very much.
Yeah. Now we're moving on to our next talk, or the next speaker is Dr. Constantinos Kolias. He's an assistant professor at the University of Idaho. Dr. Kolias joined the computer science department at the University of Idaho in 2018. Before that, he served as a research assistant professor at the supervision of Angelos Stavrou in the CS department at George Mason University. He received his doctorate in 2014 from University of Aegean under the supervision of Georgios Kambourakis. Hopefully I pronounced it correct. His main research interests revolve around security and privacy for the Internet of Things and critical infrastructures. He is active in the design of intelligent intrusion detection systems with a special interest in privacy-preserving distributed IDS. Currently, Dr. Kolias aims to design an easily deployable, completely external, and non-intrusive anomaly detection mechanism that is based on the analysis of electromagnetic signals emitted by a target device. More specifically, Dr. Kolias and his team focus on capitalizing and developing novel generative methods for the development of novel code-to-EMsignal generation. Other areas of interest include mobile and wireless communication security and privacy enhancing techniques in the internet. In 2015, he created and released the first wireless dataset specifically intended for wireless or research security, namely AWID dataset. Today, AWID has been downloaded and used as a benchmark by hundreds of organizations and universities. Dr. Kosters, thank you so much for joining us this evening here at UND as part of the virtual workshop. The floor is yours, and hopefully you can hear us.
Yes, thank you very much for the kind invitation. I am trying to share my screen right now, and I think I managed to do that. Yes, and most probably you will see everything in presentation mode.
Yeah, we're good. Thank you.
Right.
Go ahead.
Thank you very much for inviting me. And I'll try to keep this presentation short and very high level, just because I know that a lot of people don't really like cybersecurity, and I'm a cybersecurity person. Typically, especially when it comes to deployment, cybersecurity is an afterthought, as we have seen in practice. And people, especially engineers, tend to freak out when it comes to cybersecurity because it reduces their revenue. Not only engineers, but other positions as well. So in this presentation, I'm going to talk about grid cybersecurity and cyber resilience. And I will explain a mechanism, very simply oversimplified for the purposes of this presentation, mechanism that recently has been published that has the potential to increase the resilience of smart grid infrastructures. But before we move on, let me do a small, very brief introduction and say that today, the power grid is organically growing over centrally controlled power systems that we know, and it's becoming a massively interconnected cyber-physical system, essentially, with advanced technologies regarding the fast communications, the intelligence, which include, obviously, the Internet of Things, smart meters, interconnected electronic devices of all sorts. And while this convergence is significant of all these devices, a significant number of cyber-physical elements has enabled the vision of smart grid. And it has allowed us to hope that smart grid can become and can be far more efficient and competitive, especially when it comes to addressing the growing global energy challenges. Unfortunately, it has also introduced a large number of vulnerabilities in the cyber physical space, particular, which result in violations of data availability, for example, integrity, as well as confidentiality, which is the triad that the most cybersecurity people are interested in. And according to the vulnerability reports from US CERT as well as Kaspersky, the energy sector has reported the greatest number of vulnerabilities among all network infrastructures. These figures that you see here shows the number of vulnerabilities of various industrial control systems between 2010 and 2019. Accordingly, 178, 110, and 283 cyber attack incidents were recorded in the energy sector alone, out of a totality of 300 approximately, 400 approximately, and 500 approximately ICS cyber attack incidents altogether. These cyber incidents may lead to countless security risks, including loss of critical data that are necessary for control operations, malicious modifications of critical power system states. We all know about false data injection attacks. We have heard about them. And the possible consequences in these cases may include incorrect customer billing, which is, I guess, the least of our worries. Price manipulation in the energy market, that's a more severe type of attack. And small to large electric power outage. And we have seen such cases, not necessarily in the US, but they can be very catastrophic. In the past, there have been various attacks against power grid infrastructures, at least even if we focus on the last decade alone, right? This figure demonstrates a timeline of the recent global cyber incidents, and we see several cases where the victims were located in the US. I would say that these are not the most severe incidents, but in 2019, for example, very recently, there was an attack against the distributed power control center and several small generation facilities that created, headlines and raised some concern regarding the modernization, I guess, of the infrastructures, the energy infrastructures in the US. Of course, back in 2010, we have one of the most well-known, well-documented, well-studied incidents that we are talking about the Stuxnet. And I don't know if it's very clear in this figure, but you can see that this type of attack was initiated by some sort of infection that happened out of sight, potentially by people that take care of the maintenance of the infrastructure, the secure and air-gap infrastructure. And most probably something happened and they downloaded some sort of a malware that was installed and proliferated in the IT network, possibly, like I said, outside of the premises. Some engineer brought this malware via USB. It infected an engineering workstation inside the air-gapped environment. Then from the air-gapped environment, from within the air-gapped environment, that infected the engineering workstation, proliferated the malware to PLCs. Remember that malware was designed to infect special Siemens PLCs, and that these PLCs dictated a wrong rotating speed for centrifuges that typically purify the uranium. And in this case, the outcome was just, harming the centrifuges to the point that they would need replacement sooner. So it was a type of economic, as we call it, denial of service attack. But in reality, this is very alarming because it could easily, the same malware could easily achieve a much more catastrophic outcome with the same type of resources. Okay, Stuxnet was, I guess, the wake-up call, and we have done extensive taxonomies through the analysis of different types of incidents that have happened in ICS as well as power infrastructures, and we have seen a pattern. And in this case, the pattern, it falls down to three elements. First of all, the human element. It's, I guess, the common denominator of all real-life incidents out there. It is either some malicious person, typically an insider trying to do something, or some employee that did not have enough training security-wise to differentiate between good, proper, I guess, security practices and poor security practices. Apart from that, we also see that protocols, communication protocols, have a myriad of security vulnerabilities that come to light every day, I suspect. And finally, in some cases, we have seen that we tend to have poor configuration when it comes to our network resources and poor isolation. This figure shows a very distinct areas of operation. This is, I suspect, the IT, and this is the OT. So the lower layers of the network have much more critical purpose, and they are much closer to the physical elements of our system, and therefore their misbehavior can cause can have catastrophic results. However, we have seen in practice that these two realms are not properly isolated, and that very, very often has led to severe catastrophic incidents and the proliferation of malware from the IT to the OT realm. Now, let me say a few things about the smart grid, because that's the main focus of our studies. And today, the electricity network has been, I guess, under a digital transformation from a conventional monolithic power grid into, I guess, the current arena that we call the smart grid, right? Over a decade ago, many international organizations, including IEC and NIST and ETSI, the European Telecommunication Standards Institute, developed a roadmap for the smart grid. And according to IEC, the smart grid can be defined as a concept of modernizing the power grid that, I guess, integrates with electrical information technologies between the point of generation and the point of the consumption. That's, I guess, is a very vague description of what smart grid is according to IEC. NIST, for example, according to NIST, smart grid can be defined as an electrical system that integrates bidirectional flows of energy, two-way information, cybersecurity, extensive and robust communication with infrastructures like the internet, control technologies, computational intelligence, including AI, and this sort of stuff. Now, unfortunately, as you can expect with connectivity and exposure to something that is not very regulated infrastructures such as the internet, we have threats and attacks. I mentioned before that the power sector has seen a tremendous increase in cybersecurity incidents. And I guess it's kind of like the most obvious first way out of attackers. This is what they want to attack first. And when I'm talking about attackers and malicious people, you should always keep in mind that these groups or these individuals have different types of capabilities and motives. And this differentiate is the main differentiator, I guess, at this point of one cyber incident from another in terms of severity. It is not necessarily the defenses that are employed today, and it is not the defense tools and the security hygienes. Attacks may vary in terms of sophistication and we can distinguish against, I guess, the capabilities of attackers in terms of technical skills, the tools they use, the social skills they possessed, and also the access to equipment. Finally, very often we see that certain attackers may influence or may have access to insiders. When it comes to motives, we see that in some extent they have financial motives, but in most cases it is either they are under the influence of some ideology or they have political motives. Finally, we see that indeed, up to some extent, but not necessarily, doesn't necessarily play the most important role, we have the characteristics of the system, the target itself, including the topology, the software that it has, the type of systems, and unfortunately, a lot of the vulnerabilities have to do with the very slow update cycles that we see in energy systems, the network and the architecture of the network, including the isolation, as I mentioned before, as well as the processes that are supported by each system. Before I move on, I would like to make a parenthesis and talk a little bit about a relatively new technology that has penetrated the smart grids, and that is digital twins. And I'm talking about the digital twins in this presentation, not because it is an it is an integral component of the smart grid, but rather because it's a fascinating technology that will probably be a very important component of all smart grid and ICS systems, in my opinion. But in this case, the most important thing is that our protection approach heavily relies on this technology. So back in the early days, digital twin is a little bit of a misunderstood term. In essence, it's nothing more than simulation. And we have done simulations of systems, even very complex systems, such as energy infrastructures, for a very long time. However, for the first time, the hardware capabilities and the software capabilities allow us to go to such a great depth that we can actually talk about simulations that have such high fidelity to the real systems that at this point we can describe them as the digital twins of real life physical or cyber physical systems. I guess the most important differences of digital twins from traditional simulation tools is the level of detail and fidelity that they offer, where digital twins aim for a high level of detail and accuracy in replicating the real world system and its dynamic relationships of the components. Second, I guess, is the real-time monitoring and feedback that it offers, unlike the simulations, traditional simulations, where you fire the simulator once, you wait and you receive the results after some time. We are talking about, I guess for the first time, we are talking about real-time monitoring also. And it's a design tenet of the digital twins. Real-time monitoring, providing continuous feedback by incorporating live data from the physical system through sensors that receive readings and forward them to the cyber realm, possibly some cloud infrastructure that takes care of the digital twin representation. We also have increased adaptability and the capacity essentially for learning. And one integral component of digital twins is the fact that they rely extensively in AI technologies. And from the data that they receive, they are capable of self without necessarily huge human interference to adapt to different types of situations and proceed to predictions if necessary. We have the application range, which is much, much greater in digital twins. Always keep in mind, digital twins are very generic, unlike the simulations, where the simulation simulates a very specific component of a subsystem, potentially belonging to a subsystem of the greater infrastructure that we want to monitor. Digital twins, essentially, they are much more generic. They can provide observability to different types of elements of the system, and they are not custom tailored to one specific type of simulation, right? Unfortunately, we have also negative aspects of digital twins, and they mainly stem from their complexity. It's today it's very hard to initially come up with a digital twin of particularly complex systems. It is okay when it comes to things such as a digital twin of a turbine or something like that. But when it comes to something like a factory, or when it comes to something like a much more complex system like a microgrid, we need to make a huge investment a priori. Also, when it comes to maintenance, things tend to change rapidly, drastically. Maintenance in these situations often becomes an issue. Like I said, creating and maintaining digital twins can be more resource intensive, I guess. After the first investment, the system requires an ongoing investment, and that's not very appealing in several cases, non-critical in some cases, but some applications may benefit from that. We claim, however, that it is relatively easy to come up with the digital twins, not necessarily supporting extremely high resolution or fidelity, but we claim that it is possible to construct this type of twins, and enough at least to provide some sort of a cybersecurity component on top of what is considered as traditional digital twin applications, which include predictive maintenance. So today, I guess the killer application of digital twins is to allow the real-time monitoring of machinery and equipment by analyzing data from sensors that are spread all over the infrastructure. It is possible in some cases to predict potential failures or enable proactive maintenance to prevent downtime. This is, I guess, the particular application, but we also have the optimization of processes, the management of more effective management of resources, quality control, and we have even seen in the power sector digital twins applied for training and simulation. I guess cybersecurity at this point doesn't make sense because generally it requires extreme level of depth and detail, which might be cost inefficient at this point. But as we will see in the process, we claim the opposite, that even simplified techniques and very high level implementation of digital twins can provide another level of protection and some level of resilience, enhanced resilience to smart grids. So at this point, the research question that we have is whether it is possible to capitalize on the digital twins technology to create or increase the resiliency of power grid or smart grid infrastructure. And at this point, we introduce technology that, or a strategy that we coined with the term split and destroy. And essentially, we are talking about a moving target defense technology, or a variation of a moving target defense technology, different motivations in this case. But before we move on, let me clarify that our approach indeed is based in moving target defenses. It has adopted some elements, but this type of defense does not aim to create confusion to the attackers. Moving target defenses aim to create confusion by manipulating some aspects of the system that the attacker has identified potentially as vulnerable. For example, in the past, analogous efforts have relied in the constant changing of IP addresses. That is one type of moving target defense that aims to create confusion. But in our case, our approach aims to achieve isolation, and mainly isolation in terms of malicious activity versus benign activity, and it does not focus and does not aim in creating confusion. Let me carry on a little bit and further explain what some of the basic moving target defense concepts that in a sense apply also to our system. The moving target defenses are based on the process of shuffling, diversifying, as well as adding redundancy to a system. Shuffling is a generic term, then we loosely use this term today. And generally, it is used to describe the randomization of system parameters. As we mentioned before, changing an IP or the URL of a network resource is a type of shuffling strategy, right? Diversity, on the other hand, is the reliance on components that offer the same functionalities, but in a different way. Like, for example, different hardware, different protocols, different operating systems. As a concrete example, I guess I will say that it is possible to do a rapid migration of an application from one operating system to another. Imagine that, right? Imagine an attacker that has identified that they want to target a Windows operating system running IIS, but in the exactly next time slot, they see that this system is not an IIS and it's not running on Windows operating system, but rather an Apache server running on Linux. So this is a diversity strategy that is often adopted in moving target defenses. And finally, we have the redundancy strategy, which in this context aims to provide alternative avenues for offering the same service. So if a system fails, another system that normally is similar but is configured to perform a different process can be repurposed, be reconfigured very, very rapidly to perform the original functionality that is not offered at this point. So in the past, we have done some work as part of the DARPA XD3 project, Extreme DDoS Defense Project. And we have proposed a shuffling strategy where we have potential systems that are under some sort of a DOS attack. Back in the day, our main focus was low rate attacks that apply at the application layer. So for example, if you have ever heard something like a slow RORS attack, that would be within our scope. And our goal was not only to create confusion, but also to isolate the attacker. So at least one component of this system was the same as the one that we are going to examine today. The graphic shows that a simple example of shuffling or moving target defense, as I described before. The protected system is comprised of two servers that provide normal operation, let's say a website or something like that. And each one of these two servers are under an attack by a malicious client, which is blended with the legitimate clients. So we have C1, C2, and C3, C4 are benign clients, and we have A1 and A2 that are malicious clients. The particular shuffling defense introduces two additional servers that are replica, basically exactly the same servers are the original ones, and repeatedly shuffles clients until one server is being attacked and the other server is comprised of connections initiated by benign clients. So at least 3 clients are saved in this case, and we have one client, C2, that is sacrificed as they fall to a replica server that is under attack by the two attackers, A1 and A2. And obviously, eventually, this process involves the spawning and the shuffling iteratively. And as you can guess, it can always lead to a solution. After exhaustive tries of shuffling and spawning several resources, several replica servers, we can achieve the full isolation of attackers to one machine. So, driven by this scenario and inspired by the previous strategy, we propose a variation that is based on simply the partitioning of total connections of a host to smaller replica servers. And again, when I say server or replica server, you can think of it as a digital twin of a component that is a critical component, say a PLC, that is part of a smart grid infrastructure. Such a device would normally be the target of an attack, either DOS attack or other types of attack. Some servers, for example, might be targeted for different purposes, such as the exfiltration of data. Some other servers could be targeted for ransomware, that is to encrypt their operating system, their file systems, and ask for ransom in order to decrypt it and retrieve the original data. So how does it work? Let us assume that we have a server that serves 8 connections at the same time. And of course, this is an oversimplified scenario. At some point, we realize that the server is misbehaving. And take that with a grain of salt. You can interpret misbehaving in any way you like. Let's say, for the sake of simplicity, that the server is under a DOS attack. Therefore, it is unresponsive in the time that we examine. It is obvious that one or more of these connections is responsible for this type of activity, but we do not know beforehand which one is responsible. In reality, as you see here, the connections C7 and C8 are responsible for creating the problem. So there is something that is very unique with these connections. Say they are very slow, they transmit 1 byte of information, or they even transmit malware or components of a malware or something like that. So in this case, and by capitalizing on the digital twin technology, we decide to spawn 2 new servers, and both of which are exact replicas of the original server or the original device. Again, server, device, up to you how to interpret it. The idea is very generic and broad enough to incorporate a lot of different application scenarios and a lot of different attacks. And we decide to spawn 2 new replica servers, and we partition the connections to replica 1A, as you see it in this figure, and 1B. Half of them go up and half of them go down. Immediately, you can see that all of the connections that replica 1A supports are benign. And therefore, if we check at this point to see whether the DOS attack or the system is unresponsive, we see that it is not. Everything is fine. So we conclude that the connections in this case, C1 to C4, all must be benign. And therefore, we save these connections or we flag them as benign, and we focus our attention to replica 1B because 2 of its connections, in reality, we don't know, but 2 of its connections are malicious. And obviously, if we check at this point the system, we will realize that it still is misbehaving at this point. So we proceed to a second cycle, a second iteration, where we further split these connections to 2 newly spawned replica servers, 2 new instances of the original digital twin. And again, half of the connections go upstairs, half of them go downstairs to replica 2B, and 2C. After examining the system and its behavior, we see that the 2B is perfectly healthy, and therefore we save these connections also by migrating them potentially to the original server or some other replica server. And we insist and potentially repeat the process with replica 2C, which hosts the 2 malicious connections. So from a 10-foot perspective, this is the strategy that we have adopted. And let's examine the advantages of this approach. Of course, we are talking about the oversimplified scenario. We will explain and we will consider some more sophisticated scenarios, but in the end of the day, it is, I think, easy to understand that the advantages of our proposed approach can be outlined as most probably A, it can always lead to a perfect solution without sacrificing benign connections, assuming that there is enough time, assuming we have this luxury, we will always manage to isolate and identify all the malicious all the malicious connections. Second, it can converge to suboptimal solutions very, very fast, assuming that we are willing to sacrifice some benign connections. So it is possible to stop the iterative process and say that even if we save, let's say, 70 or 80% of the connections, and we identify these connections are as benign, we are going to be very happy and we can continue business as usual, even if, let's say, 10% of our benign clients fall in an instance of the system that is under attack. Okay, and very, very importantly, it is possible to isolate even zero-day attacks. In the previous example, when I was describing the strategy, you probably didn't hear me mentioning anything about characteristics of attacks, their rate, or special structure of packets or anything like that. So for this reason, even if we have a totally novel practice or methodology of attack, the system will be able to isolate the threat as long as we are able to get feedback regarding the state, the health status of our system. Finally, it does not rely on sophisticated intrusion detection tools. Obviously, we assume zero knowledge of the attacks. However, we have done some experiments regarding the benefit of incorporating intrusion detection tools and on-the-fly analyzing patterns of connections and packets and network traffic. And we see that it drastically improves the both the timing as well as the consumption of resources. So what about the assumptions? First of all, obviously, this type of strategy is not it doesn't apply to everything. However, when it comes to long-lasting connections, most probably you can sense, including false data injections or low-rate DOS attacks or data exfiltrations or some types of APT attacks, most probably you can understand that because they are present for that long and we have the chance to shuffle and partition these types of connections, these are the best candidates for our approach. As I mentioned before, we do not assume that we have any sort of knowledge regarding the attack. Ideally, this type of attack this type of defense applies to a wide range of attacks, most importantly, including zero-day attacks. And another assumption is that we have observable results of the attack. When we attack a system, we need the user to be able to say that somehow something is wrong, somehow we believe that we are still under attack. As long as we do that, then most probably the strategy that we propose is going to be very successful and will converge to full isolation in a relatively short amount of time, even with rudimentary approaches. Finally, one last assumption is that malicious connections tend to follow a normal distribution. That is, the attacker chooses to attack a system in bursts, not continuously, relatively short intervals. We see a spike. Generally, the system is under normal operation, but after some point, we see a spike in malicious connections. And this is the short time frame that the attacker chooses to unleash their assault. So behind the scenes, we have tried different types of implementation techniques, and we see technologies, and we see that the most important technologies that allow the realization of this system are three. One is the SDNs. The SDNs, software-defined networks, are meant for governing and orchestrating the connections and moving them inside the network from one digital twin component to another, one replica server to another, Second, the digital twins which are used for testing the effects of connections in virtualized versions of the systems that have been detached from their real-life counterparts so that they do not create potential real-life issues to the system. And we have discussed that a major enabler of the digital twin technology is the visualization technology, which also applies to exotic things like PLCs today. They can be fully virtualized, and you can easily come up with the digital twin version of a PLC. Finally, we have the live migration technology, which allows the connections to be moved, to be migrated along from one replica server to another with very, very little downtime. And without going into too much detail, a live migration is possible by incrementally taking checkpoints, and that obviously are relevant to the state of the system, right? Now, let's consider two extreme approaches regarding our defense. Let's assume that we have a server that supports 4 connections, one of which is malicious. One approach would be to create a replica server and start migrating each one of these connections serially to the replica server and examine the effects of each one of these connections in isolation. So as you see here, the replica server serves one connection at a time, and the original server still serves the majority of the connections. This is not an ideal situation. This process takes a lot of time because operations are done serially, and moreover, the number of checks regarding the health status of the system is the maximum. And always keep in mind that the health checking process is probably the slowest. I don't believe that it involves in all cases human intervention, but in some cases it might also involve human intervention, and may rely in a human expressing their opinion regarding the health of the system. However, in several attacks, we have considered and we have seen that checking takes around 100 milliseconds. That is the average for different types of attacks, different types of use cases that we have done behind the scenes. Another extreme approach is to rely on something like this. We have the original system. It serves 4 different connections, one of which is malicious. We do not know exactly which one is the malicious. Then we decide through a software-defined network to, first of all, spawn 4 different replica servers and immediately migrate each one of these connections to its own replica server. Obviously, this approach is much better in terms of time, because a lot of things are done in parallel, but at the same time, you can see that it requires maximum amount of resources, since we are spawning huge amount of replica servers, potentially, more specifically 1 per connection, which obviously is inefficient, right? So these are kind of like the 2 extreme cases, and we will aim to achieve a trade-off approach regarding the time and the resources required that falls in between these 2 extremes. A very rudimentary splitting technique is the following. You can assume that we have a server, and we create at each partition step, we divide 1 instance into 2. This is static. Obviously, this is not optimized, but this is a very rudimentary splitting technique. So we start from 1, we go to 2, then 4, then so on and so forth. As we have said before, these are the types of the amount of malicious both malicious and benign connections that fall under a server at any given point in time. And you can see that, especially from empirical observations, the distribution of malicious connections follows something like the normal distribution, like bell curve. And this is very advantageous for us, and we can take advantage of that, so we can optimize the system, the rudimentary approach that I described previously. In this case, for example, we can start with a very rough splitting of everything. You will see that if we split to 4, a lot of connections will be identified as healthy and exit our consideration. And we can immediately see that the majority of malicious connections will be focalized, will be around this area. And this is where we can go further and start splitting more aggressively and create more instances, because we expect that somewhere here will be the majority of malicious connections. And obviously, I was referring to this graph. I think I was stuck in a different slide. And I was explaining that this is the total number of connections, and they follow a normal distribution. And this is where we expect to see the majority of malicious connections. And this area will be quickly isolated, as well as this area, from our early partition stages. And we can do more aggressive partitioning with much more replica servers later on here in this area. So by following our rudimentary approach, you can see the distribution of connections to replica servers over time. And you can see that initially we have very few number of replica servers, that each one supports a large number of connections. Some of them indeed have more malicious connections than others, but as the splitting iterations progress, more replica servers are spawned, and the connections, benign and malicious, are distributed across these replicas. You can clearly see that the distribution, the normal distribution of malicious connections is maintained, especially as the epochs progress. Therefore, as I mentioned, we can come up for advanced stages of our approach. We can be much more selective. We can focus our attention somewhere in the middle and do more aggressive splitting or some other variations. So let's take a look at what to expect. We have done simulations based on MATLAB and Python, and we have seen that the time to reach full isolation of malicious connections, again, even if we don't have any idea regarding what constitutes a malicious connection, but judging solely on the effect of connections to our system, we can see that by adopting a very rudimentary, as you see here in the graph on the top, compared to a more sophisticated type of strategy, we can expect that for a certain partitioning step around 4 to 10, especially when it comes to 10,000 connections simultaneously served by a single host, a single component of our system, we can expect that within 200 minutes, we can achieve full isolation of our connections, benign versus malicious. By adopting a more sophisticated dynamic technique where we readjust the partitioning step according to the number of connections saved, benign connections saved, we can achieve, it doesn't improve that much, we can achieve around the same type of efficiency. So bottom line, our conclusion is that for very high number of connections, that is 10,000 per host, we can hope that around 200 minutes is what it takes to fully isolate 10% that we assume to be the pollution factor, that is the malicious connections, that is 1,000 individual connections to be fully isolated. When it comes to a smaller amount of connections, like 2,000, we can achieve the same full isolation of benign versus malicious, assuming a pollution factor of 10% in less than 30 minutes, very, very close up to 20 minutes. That, once again, by taking advantage of digital twin technology and having no knowledge of what constitutes a malicious connection. When it comes to cost, during our process, we can see that in the best case scenario, we rely on 2,000 replica servers. And when I say 2,000, obviously some of these replica servers can be repurposed. In cloud environments, replica servers that can be potentially Docker container instances of or smaller scale virtual machines that costs $10 or even less for 1 hour of operation. So this fact, which again is not very optimized as we can repurpose all virtual machines, it looks extremely large, but in reality, we are talking about tens of dollars of expenses in terms of virtual machine utilizations. Now, a very interesting graph is the connections saved per epoch. And with this, I will close and ask questions from the audience. We can see that in this scenario where we have, we consider 10,000 connections, 9,000 of which is benign and 1K malicious, we can save 5,000 connections in around 2 epochs, which is around, in practice, in real life terms, around 20 minutes. We can achieve the same for 60% or more than 60% in 4 epochs, for 70% of the connection in 6 epochs, and around 80% of the connections in 10 epochs. For achieving full isolation of all benign connections, we will require 14 epochs. So indeed, as we progress and as we filter the last remaining few connections that are benign versus the malicious ones, we will require more time, and we will have to insist and apply more sophisticated techniques. So with this, I will just say thank you very much. And at this point, I would like to receive questions if you have.
Thank you, Dr. Kolias, for your time and a great presentation. So I think we have some questions. How can cyber deception help alongside moving target defense?
How can cyber deception?
How can cyber deception help alongside moving target defense? Can they both be, and sometimes some papers talk about cyber deception, one form of moving target defense, but I think, can they work together alongside?
So I would say that moving target defense is a form of cyber deception. Notice that a large family of moving target defenses aims to create confusion or make the attacker think that one thing is going on, while in reality, another thing is true. So there are several types of moving target defenses, as I mentioned before. I would say that deception is part in reverse. Cyber deception generally is something that potentially an attacker would employ as part of their artillery. But in reverse, a defender can also do the same to create confusion, to buy more time, buy more resources, or mitigate the effects of an attack. This is basically the inspiration of the proposed technique. However, we do not aim to create confusion in this case. We aim mainly to create mitigation, to increase the resiliency of the system by isolating what is benign from what is malicious, even if we do not have a priori knowledge of what constitutes malicious activity in this case.
Great. Thank you. In your slides, you talk about, building multiple replica servers as one type of defense mechanism, but computation, that's expensive solution, right? So are you saying that there is a room for, in terms of research, even someone looking at even optimal placement of these servers?
Yeah. So a lot of people have this misconception in a sense. In reality, the advancements of virtualization and especially containerization have allowed us to hope and actually to do much better utilization of resources when it comes to building replica servers on the fly. So when you hear me saying that it is possible to spawn a replica of a server, say an Apache server, as the one that we used for our experiments, and on the fly move its state and its connections to the replica server, this is possible in under 10 milliseconds. We relied in replica servers that are based on containers, more specifically Docker containers. But the same can be used with mini virtual machines, tiny virtual machines, or this type of technologies that can allow us to spawn minimized versions of the original system. Obviously, the replica servers that we spawn will not be able to handle the totality of the connections or the totality of the effort, the load that would fall in the original server. But it is totally possible to handle some of the connections and offer a very low latency to the eyes of the user service and experience very, very small drops in the quality of experience overall by even migrating the actual content, the actual state, the memory, the entire memory, or to put it better, the parts of the memory that are important from one virtual machine to another. So to answer your original question, it seems that it is very computationally inefficient in terms of time, but in reality, it is not. If you rely in state-of-the-art technology, virtualization technologies. However, what is for sure inefficient is the consumption of resources, especially in terms of memory.
Super. Thank you, Dr. Kolias, for your time. I think thank you again for participating in this workshop. That concludes this session, and we will send you a nice plaque for your time. Appreciate it.
Thank you very much.